Good day everyone. I am Rian Bactong and these are the continuation of the report of Mr. Manyosa, and our topic is all about galaxies. Now let us proceed to this classification of galaxies. Almost all current systems of galaxy classification are outgrowths of the initial scheme proposed by the American astronomer Edwin Hubble in 1926. In Hubble's scheme, which is based on the optical appearance of galaxy image on photographic plates, galaxies are divided into three general classes: ellipticals, spirals, and irregulars. Hubble subdivided these three classes into finer groups. Galaxies exhibit a variety of size, but they come in variety of shapes as well. Elliptical galaxies are rather smooth, having no distinct features like a spiral galaxy does. Ellipticals, which account for about one-third of all galaxies, vary from nearly circular to very elongated. They possess comparatively little gas and dust, contain older stars, and are not actively forming stars anymore. The largest and rarest of these, called giant ellipticals, are about 300,000 light-years across. Astronomers theorize that these are formed by the mergers of smaller galaxies. Much more common are dwarf ellipticals, which are only few thousand light-years wide. Elliptical galaxies can be defined as a sort of dying galaxy. The next one are spiral galaxy, and spiral galaxies appear as flat blue-white disks of stars, gas and dust, with yellowish blotch in their centers. These galaxies are divided into two groups: normal spirals and barred spirals. In barred spirals, the bar of stars runs through the center bulge. The arms of barred spirals usually start at the end of the bar. Instead of from the bulge, spirals are actively forming stars and compress a large fraction of all the galaxies in the local universe. Spiral galaxies, on the other hand, have a between young and old star. This because it has a lot of gas and dust that fill the disk of the spiral galaxy. The disk formation is the main source of new star formation. These seem to have rich ingredients of the continuously creating new stars, so spiral galaxies can be known as the younger and fresher galaxies. And lastly, some are called irregular galaxies, and these are ones that don't really fit into the other two categories. Regular galaxies, which have very little dust, are neither disk-like nor elliptical. Astronomers often see irregular galaxies as they peer deeply into the universe, which is equivalent to looking back in time. These galaxies are abundant in the early universe before spirals and ellipticals developed. Aside from these three classic categories, astronomers have also identified many unusually shaped galaxies that seem to be a transitory phase of galactic development. These include those in process of colliding or interacting, and those with active nuclei injecting jets of gas. The irregular galaxies are simply more chaotic. They can often be bright, they can have young stars, and therefore they have recent bursts of formation. But again, irregular galaxies can just be known as a galaxy that isn't quite elliptical and spiral. These are the three main categories for galaxies, which we can abbreviate as ENIRR. These are also subcategories within them. Spiral galaxy can be barred spirals, represented by SB, which are ones whose spirals arms extend from the ends of a central bar rather than the center of the galaxy. There are also galaxies comprised of a thin disk without any spiral arms, and we call this S0. So in addition, true spirals can be subdivided into SA to SD depending on how tight or loose the arms are, and ellipticals can be subdivided into E0, E5, and E7. So depending on how spherical or flat the shape. So beyond displaying a wide variety of sizes, different galaxies also differ in the type of stars they contain. So elliptical galaxies contain predominantly older population 2 stars, whereas spiral galaxies contain a mixture of population 2 population 1 stars too, so many younger stars can also be found. So this due to regions of gas and dust of high density in the spiral arms, which allow new stars to form. So another are active galaxies. So in active galaxies, there are 4 types of active galaxies. These are quasars galaxies, blazars galaxies, Seyfert galaxies, and radio galaxies. So Seyfert galaxies are active spiral galaxies. Its nucleus has bright emission lines, including visible wavelengths. The nuclei of these galaxies change brightness every few weeks, so we know that the objects in the center must be relatively small, about the size of the solar system. So, next are quasars, or the most energetic objects in the universe. There are distant star-sized energy source located at the centers of galaxies that shoot jets that travel close to the speed of light of the extreme. So brightness of quasars can fluctuate over day-long periods. The word quasar is short for quasar-stellar ratio. So next are blazars, are just quasars, but type of we observe may depend upon our viewing angle than structural differences. When the jets upon happen toward Earth, it's considered blazars. And finally, radio galaxies are galaxies that emit radio waves. They are elliptical, and their nuclei emit jets of high velocity gas above and below the galaxies. So, active galaxies are galaxies that have a small core of emission at the center of an otherwise typical galaxy. So this core is typically highly variable and very bright compared to the rest of the galaxy. So for normal galaxies, we think of the total energy they emit as the sum of the emission from Earth of the stars found in the galaxy. So, but in active galaxies, this is not true. So there is a great deal more method energy in active galaxies than there should be, and this excess energy is found in the infrared, radio, UV, and X-ray. So these regions of the electromagnetic spectrum. So this energy emitted by galaxy, AGN for short, is anything but normal. So most is, if not all, so normal galaxies have a supermassive black hole at their center. So in an active galaxy, its supermassive black hole is accreting material from the galaxy's dense central region. So as the material falls into toward black hole, angular momentum will cause it to spiral in and form into a disk. So this disk, called an accretion disk, heats up due to gravitational and frictional force at work. So models of active galaxies also include a region of cold gas and dust. So true to be in the shape of a giant donut with a black hole and accretion. This nestled in the donut's hole. So in about 1 of 10 AGN, the black hole and accretion disk produce narrow beams of energetic particles and ejects them toward and upward in opposite directions away from the disk. So these jets, which emerge at nearly the speed of light, become a powerful source of radio wave emission. So the properties of an active galaxy are determined by the black hole's mass, the rate of accretion into the black hole, whether or not it has a powerful jet, and the angle at which we view the galaxy. So radio galaxies, quasars, and blazars are AGN with strong jets that can travel outward into large regions of intergalactic space. So some of the apparent differences between types of AGN are due to our having different orientations with respect to the disk. So with blazars and quasars we are looking down the jet. So active galaxies are intensely studied at all wavelengths. So since they can change their behavior in short timescales, it is useful to study them simultaneously at all energies. So X-ray and gamma rays observations have proven to be important parts of this multi-wavelength approach since many high-energy quasars emit a large fraction of their power at such energies. So the X-rays and AGN originated from very near the black hole, so occurring in the central engine. In addition, gamma ray observations alone can provide valuable information on the nature of particle acceleration in the quasar jet and clues as to how the particles interact with the surroundings. And that's all our report. Thank you.